Morning everyone. Let's get started. So today Nancy couldn't be there and Segu as well, so I'm just trying to proxy for them. So today Yan Liu and Yefan from NCSA and University of Illinois are going to discuss their ECSS project with Professor David Tarboton on establishing TauDEM as a science gateway. They're this project has been going on now just finished their first part and they're requested for the renewal. So they're going to talk about both on their optimization side as well as what their plans for their setting up the gateway and their work. Yeah, Yan, please go ahead and get started.
Thank you, Suresh, for the introduction. Hi, this is Yan and Ye. We are part of the ECSS team. Today we're going to present TauDEM as the ECSS project. This work is a joint work with the TauDEM team in Utah State University and the Open Topography team in San Diego Supercomputer Center. Well, sorry for missing the center word on the title. So this project the ECSS effort was initiated by TauDEM PI, David Tarboton from Utah State University. And the original goal was to scale the code to thousands of processors. They were able to run only on a few tens of processors on their local cluster. So they came to XSEDE, applied for a startup allocation, and the original goal was to scale the code. And we'll introduce the outcome of this part of work. And then later, this work got expanded because TauDEM is a widely used community code for hydrological information analysis. So we extended the ECSS work to actually include two parts of the Science Gateway development. I'll introduce one of them, which is the CyberGIS TauDEM Gateway application development. Some background on this science. So DEM is in geospatial is the digital elevation model. You can think of that as an image, a spatial image. Each pixel of the image represents an attribute value. So for elevation, the value of the pixel is just the elevation value. And the cell size the pixel size defines the resolution of the DEM. For example, I kept saying cell, that's the term in geospatial world too. Okay, if the cell size is 10 meter, it means 1 pixel of 10 meter by 10 meter is a pixel. It represents the area that this pixel attribute have. In elevation data, the elevation value is usually a floating point in meters. For DEM-based hydrological information analysis, we take the DEM, the image, and based on the elevation value, there are a lot of information can be extracted, like water flow direction, contributing area, and the stream network. And this analysis, though, is both data and computing intensive. Data-wise, as survey technologies advance, for example, government is producing finer and finer resolution DEM image. And for example, from USGS, they are producing 1 meter resolution DEMs, which for the whole US coverage will have 4 to 5 petabytes of data. Even for the current resolution, 10 meter resolution, we have 330 gigabytes of data. And the DEM-based analysis also is a set of complex algorithms, and it takes a lot of computing power to handle each analysis. So let me just give an example of this concept of the DEM-based hydrological information analysis. This is a preview of the USGS 10-meter resolution elevation data for the whole, for the continental US coverage. And you can take a portion of the data that's on the left diagram that denotes the elevation. And using the DEM analysis, you can actually derive the water flow direction and stream network denoted on the right diagram. So this is the overall process, but the software we use, there are desktop software, there is this TauDEM software, which is a parallel computing solution. It is written in C++ using MPI, and the parallelization strategy is quite straightforward. It's based on the decomposition of spatial domain. So each process handles a sub-spatial domain and exchange data with neighboring processors when necessary. And both point-to-point communication and MPI collective communication calls are involved. And there can be a lot of these calls in order to accommodate some of the iterative methods they develop. And the input and output, TauDEM also developed an in-house solution using MPI-IO. That's where major computational bottleneck was when we took over the code and did the performance profiling. The whole package of TauDEM has a lot of functions. Each function listed on the left panel is a standalone MPI application. And each step actually has a dependency on one or more previous steps. So it is kind of a computational workflow type of thing. This is a desktop level interface, and TauDEM also provides the MPI version for the deployment on supercomputers. When we took over the code, the initial goal was to scale up the performance, and then we established the TauDEM as two gateway services, one at Open Topography and one at CyberGIS. It is still an ongoing work, and we'd like to share with you our experience and get your feedback. So this is the overall picture of this ECSS effort. We take the TauDEM 5.0 and did a performance enhancement and produced the 5.x. This new version is being taken by both Open Topography to provide the web service version of this software and open the door to the Open Topography community, and taken by CyberGIS Gateway as a Science Gateway application in the CyberGIS Gateway. And the main responsibility of this CyberGIS Gateway application is to integrate the various DEM resources and present a user-friendly problem-solving environment. And we are also doing some fundamental methodology research based on TauDEM. So this is the very close collaboration among several institutions, including SDSC, University of Illinois, Utah State University, and these are the project institutions and team members. We hold a bi-weekly teleconference to resolve technical issues and keep everyone on the same page. This has been critical in keeping everyone in the same loop. So next, I'll hand to Yefan to introduce the performance analysis process and our findings.
Okay, hello everyone. My name is Ye. I was working with Yan during the past few months on profiling the TauDEM suite. So TauDEM is a suite of the tools to deal with the terrain analysis, emphasizing on the topology, hydrology. Here we use the stream network and the sub-watershed, this workflow. So the reason we chose it is because first, it covers the most important modules in the TauDEM, the whole TauDEM suite. and it also includes some of the I/O intensive function like the PitRemove or some of the computation intensive procedure like the flow directory and the infinite flow directory. The workflow looks like this. So later I will translate them into actually script we used to run on Trestles and Stampede. So the previous, okay, so the TauDEM build and run was initially done on Trestles. The source code was held on the GitHub. The source code is written in C++. You can, if you want to look at the code, you can go to this link. It's written in C++ and it has a source code directory. The hierarchy of the code is quite flat. So because it consists of multiple small modules, they may share some common header file, but they perform individual tasks. So it's very easy to isolate different functions from each other. There's also a prepared mixed-out template there, so it's quite easy to do the build. And on the Trestles initially we use when we built the code, it was the MRPG to InfiniBand 1.5.1 was the default is a default implementation. So we use that. We also specified some other parameters just for optimization. I put a screenshot here, basically demonstrate the script we use to run the whole workflow as I showed in the previous slide. It consists of 9 steps. Some of them, like the first step, is I/O intensive. Some of them are computation intensive. Next slide, please. Okay, so in the whole process, we categorize the profiling work into 4 major parts. We started with the I/O profiling because TauDEM is dealing with large amount of data. We are talking about several, maybe 100, more than 100 gigabytes data. In the I/O profiling phase, the largest data set we were using was around 36 gigabytes, which shows some of the problem, the communication pattern or the I/O problem of the code. We haven't been able to escalate them over 100 gigabytes, but that's our future test. The second step we were focusing on was the MPI communication profiling. We basically want to know the communication time used in the code. We want to see how the MPI is being used in TauDEM. Then we perform the code tuning. Basically, we read the source code. We perform some software engineering practice there. See if it's friendly, if every pointer was every memory allocated was handled correctly. And at last, we did some very simple analysis on algorithm. We read the paper describing some of the algorithms and see whether it's the best way to parallelize it. So the data set we have been using are basically these 4 data sets. We started with a very small one. It's only 7 megabytes. It's basically for validating the change of the code, because every time when we change the code, we need to make sure the behavior of the code is correct. But it doesn't make sense if we run it on a very large data set. So the TauDEM team provide a simple script to basically compare the correct result with the result we get. So by doing this, we know whether our change is valid, whether the code is built in the right way. We later ran it on the Yellowstone, which is a 2 gigabyte data set, and then on Chesapeake, which is 9 gigabytes. And at last, we ran it on the USGS national elevation data. It's a 36 gigabyte. We downloaded the dataset from the USGS website and did some pre-processing to make sure the TauDEM can recognize those inputs. That was done on Trestles. Next slide, please. So the multi-file input model, as we know, so the TauDEM is based on the input of TauDEM is based on TIFF file, which is a raster image file. It has a limitation which is 4 gigabytes. That's making this multiple file input model very important for TauDEM, because if we are dealing with a big domain, the size of the TIFF file can easily go up to more than 100 gigabytes. So in the current way that TauDEM deal with the input is that if you have multiple inputs in the graph, the red rectangles represent the input file. So basically, all the input file, the input GeoTIFF file, compose a big domain. And after read this data into after TauDEM read this data, the TIFF-IO, it will cut them, decompose them into different straps. Here we use just 5 processors as an example. So you can see there are the four blue lines. Basically, have 5 straps. 5 straps in the whole. The 5 straps that compose the whole domain. You may notice that in a single strap, the data can come from different files. So that doesn't have to be like one file corresponding to one strap. So next, let's talk about the output model. So since we have read the data into the code, we have read them into the memory, we process them. When we output, there's 2 options. If we use that, we can use -m app to specify the output, the way to output the file. If we just use 1.1, then the processor will just write the strap itself is dealing with. You can specify make it more complicated. For example, in this example, we use -m app 3.2. Then it will divide or decompose its strap into 6 parts, which is 3 columns, 2 rows evenly. In our profiling work, we mainly using -m11 because we want to make this simple. So the reason we want to do the TauDEM profile is because it has poor performance previously. On a 2 gigabyte DEM, it took around 700 seconds to run on 8-core desktop. That's for the PitRemove, which is the very first step in the workflow. If we escalate that run onto the 64-core cluster with the exactly same code, the runtime goes up to 4,000 almost. So the scalability of the code is pretty bad. So the interesting part of this work is you have to both have knowledge in the high performance computing as well as the domain knowledge, the geography knowledge. Next, please. So we start with the I/O profiling with Darshan since we think this is the most important part. So from the graph on the right, we can see that there are a large amount of read process, and the red bar represents the read and write, the total read and write. The blue bar represents the consecutive read and write, while the green bar represents the sequential read and write. So here, 2 things are noticed. First, the read is the amount of data is much larger than write. Also, it's not demonstrated in this graph, but all these read are very small. So we are just reading a small part of the small part in the file. Also, what we have noticed is that all the I/O operations formed with MPI/IO are in a non-collective fashion. This might be a bottleneck because they are treating each file independently. Suppose we have multiple process reading from the same file, that could cause congestion easily. So next step, we move to the profiling, to the benchmarking. We ran the PitRemove on Trestles using the Yellowstone dataset, initially with their parallel file system master. As we can see in the graph, the scalability is bad. Basically, with the increase of processor number, the processing time goes up. Also, if you notice, if we put the data write, data read, and header read together, this part of the I/O time is dominating the whole processing, while the computing time is just a little portion comparing to the I/O time. Next slide, please. Since we know the I/O is a problem, we want to see how it's performing on the SSD, the solid-state drive, because we know solid-state drive is very fast on the I/O operation. So we did it right on the Trestles. Trestles has some node with some local SSD disk. The drawback is all this SSD is local, so we cannot run across nodes. So we just did test on a single node. So the left side is the run on Lustre. The right side run is on the local SSD. As you can see, it's got a tremendous better performance on the SSD, which improves our assumption that the I/O is a big problem here. So we dive into the TauDEM code. We read the TIFF-IO. They write their own. They were writing it based on the TIFF-IO library, the open source TIFF-IO library. They just put the MPI I/O there. The problem we found is that so all the process are trying to read from all the TIFF file, all the input TIFF file, to determine the domain they are assigned to. If you remember the previous graph, there was the different files. They compose a big domain, and this big domain was getting into straps, and each processor will deal with a strap. So how does the processor know which strap he is responsible for? So the previous solution is to just let every process read every TIFF file, the header file of the header information from the TIFF file, and to determine where he is at. But this is definitely not a good solution, because if we have, say, we have 10,000 of process reading from 10,000 files. In the operating system, we will have 10,000 by 10,000 file descriptor. That's file handler. Our solution was to just let one process gather all this information, do this partition, and broadcast this result to all the other processes. So at the same time, only one process are reading from all the files, and later, if we can partition the input file well, every process just needs to read data from one file instead of from multiple files. There are also some other problems. Here we found that, for example, they open a lot of files, but they forgot to close the file. Because in one of the test run, we found that the program fails. The program fails when too many files are being opened. Next slide. So after we did this change, the scale on the PitRemove starts getting better. As we can see, the time first, the computation time is dominating now. That's what we want to see. The overall performance, the scalability is getting better, but it's still not as good, because we think this is because PitRemove is more of I/O intensive. It's not computation intensive. Also, if you notice that after we reach the 128 cores, the performance gets pretty bad. The reason for that is Yellowstone is a kind of small data set. It's only 2 gigabytes. If we divide them into like 500 processors, each processor will only have a very small domain to deal with, which makes the communication time a lot. Actually, I need to mention here that the computation time here, the bar in the kind of blue or green, sign. It also includes the communication time. So we suspect that most of the time was consumed when we do the MPI stuff. Next slide. So with the same change, this data flow directory is a computation intensive program. We can see exactly what we want to see. For first, the result flag is actually the communication part. It's taking most of the time, and if we look at the performance boost, by increasing by doubling the number of processes, basically the speed up is like 1 time. It's not that good, but that's what we expect. However, we still see this turnaround around at 256 cores. The explanation is the same because the data set is not that big enough for that many processors. After that, we did some we did run the Yellowstone. We have also run the Chesapeake. At last, we ran the large DEM data on the Stampede, which is the USGS NED data. It's 36 gigabytes. On Stampede, since there's we cannot run multiple consecutive IB runs in a single job. We have to that job dependency provided by Slurm job scheduler. It's still under development. We just didn't push it onto the CyberGIS production gateway, but we have a running version here. The problem is in the previous Trestles run, we just need to submit one job and get everything run. But here we have 9 separate jobs, so each of the jobs has to wait extra time in the queue. This is causing some overhead. Next slide. So the next thing we do was the MPI communication pattern. So here we use the PurpleSuite profiling. PurpleSuite is a profiling software developed at NCSA based on PAPI, and what it do is it monitors this PAPI total cycle event, and it checks the program stack every fixed cycle. Here we use 10 million since the current CPU is very fast. By doing this, we can find out where the hotspot is, where the function is stopping at. It's taking most of the time. The trick is you have to use the -G to put the debug information into the executable. So it will point you to the exactly line that takes most of the time. In our case, it's actually the MPI synchronization. Next slide, please. So this is the result we get from the PurpleSuite. So this is the USGS NED 36 gigabyte run on Stampede. It's using 1024 cores. The blue line represents the total CPU count, as I explained in the previous slide. Please refer to the left vertical axis. The red line is the total consumption, the percentage in MPI communication. Please refer to the right vertical axis. I sort this by the CPU count, so you can see the blue line is going up. One interesting thing is the red line is going down, which means from the very left side, you can see the MPI percentage is around 90%, while on the right side is around 40%. Here we have two assumptions. The first thing is by the big variance in the CPU count. This big variance, that means the job is not. So basically, this parallel processing is imbalanced. Some of the processor are having too much computation work to do, while some of them are basically idling there. That also actually explains why the MPI percentage is very high for those processors with the lower load. So because if we transfer the same amount of data, if you are processing less data and you are transferring the same amount of data, the percentage used in the MPI part will be significantly higher. Next slide, please. So we've also, to prove this, we've also used the Intel VTune tool to profiling on local desktop. We focus on the DXflow directory. The result flash function we're taking most of the time, and by looking into that function, we found that the program stalls at the data synchronization part. This is partially the nature of how DXflow directory algorithm works. So basically, it's based on it's iterative processing. So every process has to stay on the same page. Basically, after one iteration, they need to synchronize the data on the boundary, and they need to know what's happening on their neighbors, and they need to check some value to determine whether they go on this iteration. So that means processors have to wait on each other to get into the next iteration. Also, that proves that if we have some load imbalance issue in the input, that would dramatically drag the performance. Next, please. Yeah, with that, we look at some of the TauDEM algorithm. So we found that in some case, in most of them actually, the data synchronization on boundary is inevitable. And we have the synchronization was done on every iteration. We think this is not very. This can be improved because it's like a broadcast. The way the algorithm works is like a broadcasting process. So the boundary data will get changed at the very late stage during the computation. And since the processors exchange the data on the boundary, so it doesn't make sense to do the synchronization at every single iteration. We can come up with a smarter way to do this data synchronization. Also, the original algorithm was written in a sequential fashion, so it was not read in the program in the parallel programming model. But that's a pretty big research topic. We think that there may be some way that we can fundamentally change the algorithm to utilize the power of parallelism. Next, please. So at last, we also did some code tuning. That includes, for example, we make some, since the code is written in C++, we make some frequent call function inline. We remove some inheritance to make sure the static dispatch enabled instead of the dynamic dispatch on some critical function. Here, the definition of critical function is those functions that are being called a lot of times. We also, for example, combine the MPS send followed by MPI receive to a MPI send receive. We also found some potential memory leak because the unmatched delocation. So, for example, some pointer was some allocation was done, but later it was not filled correctly. We've also done some change on the indent, the appearance of the code to make it more friendly to the future developer. Basically, that concludes our effort in the profiling part.
Thank you, Ye. So in summary, the performance analysis was quite a comprehensive, covering communication, I/O, and computation. We already eliminated the major I/O bottleneck, and we are working on computational, that's the algorithm, the potential new algorithm design, and the communication part to remove unnecessary data exchange among neighboring processors. So next, I'm going to talk about after these improvements, we took the code and released a new version in GitHub, and we took the code deployed on Trestles as well as on Gordon for the development of Science Gateway applications. The open topography part, actually, we published an abstract at XSEDE 14. I encourage you to read the paper written by Chunhan, Yun, and Nancy. to know the details of the open topography part. Today, I'm going to quickly cover the CyberGIS part. So when we take the TauDEM as the application for CyberGIS integration, we follow the streamlined integration framework, which I will introduce next. And currently, we already released the beta version in August, and we are developing a course-ready version this month. That's going to be used by online course taught by TauDEM team, the PI, and the instructor from Texas Austin. So we defined this application integration framework in CyberGIS to streamline the application integration process. CyberGIS software environment includes three modalities. The gateway part, in GIS world, people are familiar with the visual interface. They don't want to deal with scripts. So for every application we develop, we have to make very interactive user interface components in the gateway. And we have a library, mashup library for that. And GISolve middleware is sitting between gateway and the backend, the cyberinfrastructure, to bridge them. Basically, in CyberGIS middleware, we have a service-oriented environment. We have a database and a controller monitoring all the events. And we have services, the cyberinfrastructure services, including job, data, and visualization. We also have a set of metadata service, data service, mapping service, visualization service hosted in our local virtual machine farm. The CyberGIS toolkit has two parts. One part is generic to set up the computing environment and provide a generic job wrapper to actually wrap the input and output of each analysis. And we also have, for each app, wrapper script that's particularly designed for integrating the data from multiple sources, the code that takes the data and process the visualization, map projection, those particular spatial analysis needs in this wrapper script. So our design of the gateway, I probably mentioned this before, a lot of venues. I'd like to just brief here. There are threefold. First, this is an online problem-solving environment for GI scientists. They don't want to deal with a script, so this online environment provides a way for them to do a shared analysis on large-scale analyses that they cannot do on desktop. We also want to provide easy access to the backend cyberinfrastructure by transparently handling analysis without exposing details of where to run, what's the supercomputer characteristics. That's hidden behind by using the GISolve middleware. Also, the nature of this GIS application requires a rich set of highly interactive user interface components. So technologically, we have to choose a web development framework or technologies to accommodate those needs. We have several characteristics of the gateway: usability, scalability, interoperability with the service environment, and sustainability. That's our requirements. The design approach, we take the rich client web portal development approach, which we use quite a set of JavaScript library on the front end, and the model view controller model we take. It's also on the client side. It's not on the server side to facilitate the flexible rendering of the web content in the browser. We also developed each component into a module so that it can be easily integrated and taken in and out to or from the gateway environment. To interact with the backend GISolve middleware service environment, we developed an open service API approach to provide a unified multi-language client API for application development and for gateway integration. The gateway portal, unfortunately, I cannot do a demo due to my operating system limitation. I'm using Linux and I cannot share the screen. But I encourage you to go to gateway.cybergis.org. You should, if you don't have an account, just register, and you can go to the TauDEM application to try out the features that I will describe next. For Gateway, the technology choice, we on the portal side, we use ECSS, and it's a mobile version called Central Touch for the development of user interface components. And on the back end, it's PHP plus the Open Service API. The mapping service we do actually is also incorporated as an ECSS component, but we use OpenLayers, a JavaScript mapping library. It's widely supported and it performs really well. On the back end, we have a set of visualization servers which use GISolve. It's also an open source Java-based mapping server to provide the visualization features for each app analysis output. For the service infrastructure, obviously we use the GISolve middleware. This is just an illustration of a typical application we develop. In this, on the right side, that's a code stub, code structure. We have this app.js as the entry door to the gateway, and in each app we have the model view and the store, which is a collection of models and a controller. And the CSS resources and other server-side scripts are hosted separately in different directories. And through this way, we can put them in a scalable way to develop more applications. Meanwhile, we develop a set of reusable components shared by all the applications as reusable JavaScript library, including the portal layout, management, user management, security stuff, and the user interface components, including the map panel, map layer handling, and legend, those geospatial components, and some common lists for jobs, data, and data uploading, downloading. All the requests generated in the browser will interact with the service environment. Once analysis is composed and submitted, we use the GISolve Open Service API to submit it to XSEDE resources. For TauDEM, we submit to Trestles. That's deployed. That's the deployment for the current version. On this diagram, it illustrates the workflow of Open Service API as an application integration and a computation framework. For any scientific code, when we take the code, we ask the authors of the code to register their application through this API so that we can know how to configure the command line of parameters, how to generate a primitive user interface. It has this whole API is based on REST protocol and a JSON format. Then we take the code to integrate. Like TauDEM, we take the code, we have to go through a manual process for performance profiling and scaling. But once we got those things resolved and deploy the code on XSEDE, we can continue on to publish the service for public access. Then users of this TauDEM application can use a computation API to submit a job, monitor the job status, and download the job output. We're also developing the data and the visualization part. So we provide multi-language client implementation in Perl, Java, PHP, Python for the Open Service API. We also have an online document to help the developers. You're welcome to try those capabilities. For TauDEM application development in particular, the major challenge we dealt with has threefold. The first is the data integration. There are so many DEM sources. The major source we use is from the USGS national elevation data. We also use open topography data, and users can have their own data. So there are a lot of sources. In each source, the data may be different in terms of spatial characteristics. For example, map projection, resolution, and the measuring units of the coordinates and the vertical value. And for data retrieval, we currently host a copy of USGS a national elevation data set at our site, which is about 330 gigabytes of GeoTIFF files. At runtime, we had to actually download them. We are looking at some data storage solutions on XSEDE or outside XSEDE to speed up this process. As we move on with the performance analysis and reduce the cost of computation, in the typical workflow execution, the downloading becomes a bottleneck that we want to resolve. One example, one possible solution is to use the XSEDE wide file system. We haven't tried that yet, so that's why I put a question mark there. For data processing, there are a series of data processing we have to do before we feed the data to TauDEM code, including the data clipping, because user doesn't want to handle the whole data set. He's only interested in the study area, and the map projection, because TauDEM, when it does the calculation, you cannot give a data set with latitude, longitude coordinates. It has to be in a distance that's in the same metric as the elevation data. Otherwise, the distance calculation is incorrect. So map reprojection, although it's a linear process, when we deal with the large data, it's also a challenge. We also have another research project called PitRemove. That's a collaboration with USGS to handle that. Currently, we're using a sequential function from GDAL library. It's the Geospatial Data Abstract library. It's a commonly used open source software. It's sequential, but right now for reprojecting several gigabytes, it takes about half a minute. But when we go to the level of the whole US data, we have to use a parallel computing solution. The second challenge is on the workflow construction, because TauDEM has, in the parallel computing version, it has 26 functions, and each function may have one or more dependency on the previous steps. So we have to present this workflow construction step in the gateway application. The solution we found and implemented was to use EXGS plus SigmaJS. SigmaJS is HTML5 library that you can draw the diagrams, graph, the links on the fly using the HTML5 canvas. And we implement that. I'd like to demo that. Unfortunately, I cannot do it today. You're welcome to try it online on our gateway. And that's the analysis workflow, but that workflow has to be translated into computation workflow on the back end. We also wrote some scripts. It's a Python script to actually construct the computation workflow. That script will be extended to support this unique way of running these standalone MPI commands on Stampede, which doesn't allow consecutive IB runs. The third part is the visualization. We usually put the visualization result on our own data storage system, then do the visualization by generating map data layers. But even the smallest TauDEM application would pop up at least 4 gigabytes of data. So we try our best to get the visualization information when we compute them. Then we carry this information back. That's the overall strategy we do. Then the visualization server's computation cost can be significantly reduced. Well, sorry, I cannot do the demo. as a conclusion, this project has been quite effective in terms of collaboration. We moved from the original goal of just scaling the code to develop two kinds of science gateway projects, one in open topography and the other in CyberGIS. And these two applications are now, the current version are both are open to public. So you are welcome to try those. And we also identified a set of development tasks for future or extended ECSS effort and even for research. So that's also a good outcome. We plan to use this application in several online courses, including one in the fall and probably several in the spring. So that also covers the EOT part. So we are quite happy about the current progress, and for development purpose, we actually are pulling in more development force into the enhancement of the current TauDEM gateway application in CyberGIS. Finally, I'd like to thank the funding agency and both TAC and SDSC. They provide Stampede and Trestles for us to experiment and for the deployment of production TauDEM codes. Thank you.
Yeah, thanks, Yan and Ye. I think it's been a great talk actually, and then a great project too. And can you please leave it on the conclusion slide, like the recommendations you have? Probably. Yeah, thank you. I think that we can have more questions too as we discuss. Yeah, and actually there's also another good example where the PI and the ECSS consultant has been very proactive in setting up a GitHub repo and trying to work it there and try to make sure the ECSS part is sustained, and lots of good outcomes and stories from this project. Yeah, with that, let me open up for questions. Yeah, feel free to ask, jump in, as the line is open for all.
Hi, this is Mona. I have a question. I know you guys said that you mentioned you use Sencha Touch as well as the Sencha EXT JavaScript libraries. I was wondering if you can talk a little bit about your experience using those products.
So at this HTML5 based web application development technology is still advancing. Currently, Central Touch and EXTJS, they tend to provide, they actually target to provide the same framework for application development, like the MVC model I introduced. But it's not 100% compatible. So they have the tool to generate the code stub, but it's separate. So you have to, when you design the interface, you have to select whether it's the EXTJS or Touch. It'll produce two sets of codes. And there are quite a bit of the incompatible components you have to deal with at this stage, but hopefully they'll converge into probably a more hassle-free product that you can generate once, and that applies to both mobile and web application. Does that answer your question?
Yeah, I think so. Did you guys compare the Sencha product with maybe any other product, say the Titanium Studio product?
That product I'm not familiar with, but we tried the jQuery mobile too. Compared with the jQuery, EXTJS product provides a set of ready-to-use components, while with the jQuery, you probably have to find some components contributed from the community, and it may take time to put them together. On the other hand, jQuery is lightweight, easy to use. EXTJS is fast. Loading time is longer than jQuery.
Okay, thank you very much.
Thank you.
Other questions?
This is John Kaz from TAC. I've got a simple question about Stampede. On one of your slides, you said you couldn't run consecutive IB runs. Can you tell me what the problem was?
That's from reading the manual. It seems that when you do the IB run, you can do multiple IB runs on different portion of the resource you have in a single request. But if I run 2 IB runs on the same set of processors, I don't think it works. Am I wrong?
At the same time? You want to run 2
No.
runs on the
No. The problem with the TauDEM is like the PitRemove. Everything starts with the PitRemove, then go to the next. But the PitRemove itself is a standalone IB run command. Then we need to run PitRemove first, then the second one. That doesn't work if I'm right on stamping.
So the PitRemove is only if it is done, the second one will come?
Yes, it has a job dependency.
And before it can't start in the same process.
I can't hear.
Suresh, can you?
Yeah, I think we couldn't hear Sudhakar's question comments.
Sudhakar.
Okay, so you are using job dependency.
Yes.
Yes.
As Ye showed, there was a dependency graph. You have to execute the previous one before you can execute the next one.
Right. So you can handle the job dependency through the scheduler.
We were trying to do for now is to use the job dependency feature of the Slurm. There are a bunch of after macro, like after OK, after any, see if we can get that workflow thing done. But any suggestions or alternatives are welcome. We are eagerly seeking the solution.
Okay. Maybe we can talk offline later.
Yeah, and also, like, I think, Matt, if you're still online, this seems to be a good thing for the workflow group to look at. Looks like maybe something like you can explore and share it with others as well.
Okay, so if you want to talk about this later, just send me email kaz@tac.utexas.edu. Okay?
Okay, I try to follow the email.
Okay, we are on top of the hour, but any other questions? Okay, thank you again, Yuan and Yifan. It's been great talk and great work on the project. So, Yuan, if you can stop sharing, I'll make sure I'll conclude the recording as well. Okay. That's it, everyone. Yeah, have a good rest of the afternoon. Thank you all.
Thank you, Suresh.
Bye. Thank you.
Bye.
Thanks, George.
Thank you, everyone. Bye-bye.